Welcome to this course on epidemic modeling. So the aim of this short course is to understand in detail the so-called SIR model. And start here at chapter 3 of the lecture notes. So in this brief lecture, we're going to introduce the simplest possible model in mathematical epidemiology. So the SIR model. And the plan of this short lecture is to state the assumptions that we make on the model, and then to discuss the parameters that are in the model. So we start with the assumptions here in section 3.1. We assume a homogeneous population. So we assume that every individual in the population is the same. We look at a fast-moving epidemic, so that on the time scale of the epidemic, the fact that natural births and natural deaths are occurring is not important. And then we also assume a closed population, no migration inward or outward. So the total population then is divided into 3 compartments. So this is compartmental modeling. There's the susceptible compartment, hence S, the infected compartment, hence I, and the recovered compartment, hence R. So you have this pool of susceptible people who can get the disease. You have this pool of infectious people who have the disease and can then pass it on to people in the S class. And then over time, people who are infected, they recover. And this another assumption here is that once you're recovered, you have immunity. So you no longer go back into the susceptible class. So because of these assumptions, this sum, S plus I plus R, is constant, because natural births and natural deaths are not important, and there's no migration. So this is constant, and we denote this by big N. This big N now will be the total population. So the model is based on a conservation principle, like what I mentioned in the first seminar. And here's what the conservation principle is doing. Because there are no natural births or deaths or migration, the only way for the population of any one compartment to change is if people in that compartment move in or out. So we now look at how these movements happen for the individual compartments. Starting with the susceptible compartment. So a person moves out of the susceptible compartment and into the infectious compartment if they encounter an infectious individual and are infected. So the probability then, delta P, that a susceptible person becomes infected in a time interval from T to T plus delta T will be proportional to the product of S times I. So obviously, if there are no infected people present, then the probability of being infected is 0. And similarly, if there are no susceptible people, then there's no one to catch the disease, so this probability will be 0. So the probability will be proportional to these quantities and hence to the product. When a susceptible person becomes infected, they leave the susceptible compartment. And then the rate at which individuals leave the susceptible compartment, just by dimensional analysis, must be proportional to delta P over delta T. So the rate then at which people leave the susceptible compartment is S times I times a constant of proportionality, so alpha. And the minus sign here is because the number of susceptible people is decreasing over time. They're leaving this class and they're moving into the infectious class. So the number of people in this compartment is decreasing. Okay, so we move on to look at the infectious compartment. And again, it's a conservation principle. So di by dt, this is the rate at which the population of the I compartment is changing. This will be in minus out, people coming in minus people leaving. So it's the rate at which individuals are entering the I compartment minus the rate at which individuals are leaving the I compartment. And I call this RR for recovery rate, because this is how people leave the infectious compartment, they recover. And again, by conservation, where are the people coming from who enter this compartment? From the susceptible. So the rate at which people leave susceptible has to balance the rate at which people enter infectious. So alpha times S times I, minus the recovery rate. Now then, the recovery rate will be the rate at which people leave the infectious compartment and enter the recovered compartment. And the recovery rate must be just proportional to I. And gamma is another constant. So di by dt is alpha times S times I, people in, minus gamma times I, people out. Okay, and moving on lastly to the recovered compartment, we assume that recovered individuals cannot become reinfected, and this rules out endemic diseases. So the only way in which the number of people in the recovered compartment can change is when people come into it. And just by conservation, people coming into the R compartment are exactly the people leaving the I compartment. So you can kind of see that up here as well, that people leaving the S compartment go into the I compartment. So there's this movement between the different compartments. Okay, so we put it all together and we get this set of ordinary differential equations, or ODEs. And you see it's a coupled set of differential equations. We have three of them, and they're all interacting somehow because this is the S equation and it contains an I. The I equation contains an S, and the R equation contains an I. So they're all mixed up or coupled. And interestingly, we can check these equations for consistency with our assumptions. So if I add up ds by dt plus di by dt plus dr by dt, it will be minus alpha si plus alpha si minus gamma I plus gamma I. So this all adds up to 0. So d by dt of s plus I plus r is 0. So really n is constant, which is consistent with the model assumptions. And those arrows that I showed you for corresponding to the movement of people between the different compartments, we again represent that graphically here. So we have the susceptible compartment, and people are leaving the susceptible compartment at a rate alpha, and this is the equation. The infectious compartment, people are entering at the rate alpha and leaving at the rate gamma and going into recovered. And there's nothing from recovered back into susceptible in this simple model because we're assuming no reinfection. And of course, in other models where you want to try and describe diseases that are endemic, you would allow for the possibility of reinfection. So that was the first part of the lecture out of the way, where I said we'd talk about the equations and the assumptions. And now I just want to talk a little bit about the parameters in the model. You can see the model has these two parameters, alpha and gamma. So I want to just talk about those in a bit more detail. And this will necessitate the introduction of an alternative parameter beta. We're actually going to get rid of alpha. So from the equations, we recognize that gamma has dimensions of 1 over time. So it's a true rate. But alpha, just doing the dimensional analysis, will be 1 over number of people times time. And you might say number of people is not a physical unit, and it's not, but we have to regard it as such for the present purposes. So then if we introduce beta such that alpha times n is equal to beta, and in other words, alpha is beta over n, then this constant beta has dimensions of a pure rate. It's a 1 over time. And so wherever I see an alpha, I will now write beta over n. So I'd like to rewrite the SIR model with beta over n. And this is somehow the standard form of the SIR model. And as I said, beta is a pure rate. And this gives us a bit more insight into what's going on, because we can decompose beta into a product, C times P. Remember, beta is a pure rate, 1 over time. So C then would be the number of contacts that an individual has per unit time. So the number of contacts between one susceptible person and the infectious class. So let's suppose the person, just a typical person in the susceptible class, is meeting 10 infectious people per day. And that's the number of contacts per day, C, and then the probability, P, that any one of those contacts leads to infection. So this observation here, or this decomposition, is the principle behind so-called non-pharmaceutical interventions. And so in the absence of any kind of pharmaceutical treatment for a disease, to prevent a disease from spreading, you fall back on non-pharmaceutical interventions. And the purpose or the aim of these is to reduce beta. And you can reduce beta in two ways: by driving C down, so you're reducing the number of daily contacts, or you're making the contact somehow safer, and that would correspond to reducing the probability P that a contact leads to infection. Okay, I want to tell you a bit about initial conditions. So this equation 1 here, it's valid for T greater than 0, so there's a start time of the epidemic. So to get the differential equations going, you need to provide some initial conditions at time 0. And the obvious ones are S at time 0 is some S naught. I at time 0 is I naught, so this is like a pool of infectious people who are present at time 0. And R at time 0 is 0 because the disease has not yet spread. So there's nobody around to be recovered. And then S naught plus I naught have to sum to N. If, for example, this is not quite right. This should be I naught. If I naught is equal to 1, so you have one infectious person around at time 0, that person is going to spread the disease. And then just the terminology for that poor individual is that he or she is patient 0. So we'll take these ideas up a bit further in the next lecture.